how rational functions work. So first question, when we solve a rational equation, what three types of solutions are we expecting to find? And maybe the way I'm verbalizing that doesn't sound, doesn't make sense completely, but I'm saying, let's just take some function that I'm just going to make up right now, like 1 over x plus 3 plus 1 over x minus 3 equals 9 over x squared minus 9. So I've got this rational equation. And what are three different scenarios that could happen when I plug a number into this?
It could end up wrong.
What?
It could end up wrong.
Right, that's one possibility, right? So it could just be that I plug a number in and the whole equation becomes false. So false if I plug in a certain number. Okay, and I'll just take a wild guess that if I plug in a billion.
Can I want to like make that question like the answer may be false if you do not plug in the solution.
Yeah, the equation will be false if you don't plug in the solution. Yeah. Yeah, it could be true. So if I choose the right number and I plug it in, the whole equation could become true if I plug in something. So a particular number, if I plug it in, the whole equation will become true. Particular number, plug it in, the whole equation becomes false. And then the other possibility is that the whole equation becomes undefined. Right? And so those are the three different possibilities for when you plug a number into an equation. So given that those are the possibilities, now our job is just to find out which numbers are which. So second question, what do we call a solution? Oh, okay, well, let me get there. So how do we solve this equation? We had two different possibilities. What can we do?
We got to make sure that the denominators are all the same.
Yeah, keep in mind, so x squared minus 9 is really x plus 3x minus 3. So how do I go about solving this equation? What was one approach?
Multiply the denominator on one side with the denominator on the other side.
Yeah, multiply both sides by the least common denominator. And in this case, the least common denominator is going to be x plus 3x minus 3. Because that's what all three denominators want to have within them, right? Like this denominator has an x plus 3, but it sees that one has an x minus 3, so it wants an x minus 3. So I would go ahead and give it the x minus 3 so that it would have a common denominator. Or this denominator has an x minus 3, but it sees an x plus 3, so it would want an x plus 3. And so I'd give it to it. And so now they all have a common denominator. And so one approach is to go ahead and just equate the numerators. So I can now say 1 times x minus 3 plus 1 times x plus 3 should equal 9. Right? So once I give everybody the common denominator, I just set the numerators equal to each other. And I have 1x minus 3 plus 1x plus 3 equals 9. And so that's 2x equals 9. And so x equals 9 halves, which is 4.5. All right? So that is the solution that will make this whole equation true. So if I plug in 4.5, then this whole equation will become true. And that was one way of doing it, is by finding a common denominator and then setting the numerators equal to each other. Okay, well, what numbers can't I plug in? What number am I not allowed to plug in? Yeah, -3 and 3. I can't plug in a number that would make a factor in the denominator 0. So 3 and -3. So if I plug in 4.5, the whole equation becomes true. If I plug in 3 or 3 or -3, the whole equation becomes undefined. And what would I plug in to make the equation false?
Any other number except for the solution.
Yeah, anything else. Anything else will make that whole equation false. Okay.
It's basically just saying, I can't tell you what the answer is, but I can tell you what it's not.
Yeah, exactly. Okay, now the other possibility of solving, other than actually finding the common denominator all the way across, is you can take the original, so that was 1 over x plus 3 plus 1 over x minus 3 equals 9 over x plus 3 x minus 3. And what was our other solution? Oh, actually that's what Hector started saying, and then I did something else. We would multiply both sides by the common denominator. So if I multiply this side times x plus 3x minus 3, and I multiply this side times x plus 3x minus 3, well, this side you can immediately see, those cancel out, and I just have 9. And over here, when I multiply this onto this numerator, what would cancel out? The x plus 3, leaving behind the 1 times x minus 3. And then when I multiply this times this fraction, what would cancel out? The x minus 3, leaving behind the 1 times x plus 3. And of course, that technique gives you the exact same thing that you'd get if you just found the common denominator and set the numerators equal. So which approach is the right approach? They're both fine. They're both totally fine approaches, and you can choose to do however you want to do it. Okay, now what do you call a solution that algebra says is incorrect, but the equation says is undefined? Like, what if I had done this equation and it said, it's true if you let x equal 3. But we also know that if you plug in 3, it's undefined. And that's called extraneous. Yeah, if the solution you find is also not allowed, then that solution is extraneous, meaning algebra took you there, but it's not actually allowed. It's not in the domain. Okay, and when presented with an equation with a denominator, what's your goal? When you have a bunch of denominators, your goal is to do what to them? Ultimately, your goal is to eliminate them, cancel them, get rid of them, get rid of your denominators, and just, change the equation into a simple polynomial. That's always the goal. Get rid of the denominators and turn it into a polynomial. How do you find the least common denominator of a bunch of fractions? Well, it's like what we just did. You look at each fraction and then look at the other fractions and see if they have anything that it doesn't have. And then you contribute it to the top and bottom. All right, and then, good one. What is the intuitive meaning for these questions, f of x less than 0? What is the intuitive meaning of that question right there?
Below the x-axis.
Yeah, when is the function below the x-axis? So right here, we'd be looking at that part. When is the function below the x-axis? So then what does f of x greater than 0 mean?
Is it above the x-axis?
Yeah, when is it above? And so then in that case, I'd be looking at whenever the graph is above the x-axis.
So therefore, when f of x equals 0, that means it's right on the 0.0 point, right?
Yeah, it's on the x-axis, which makes it an
X-intercept.
x-intercept. So that's nice. See, these three questions go hand in hand, and they reiterate the main idea that we've seen from the beginning, which is that when you want a y-intercept, you plug in 0. But when you want an x-intercept, you set the equation f of x equal to 0. And that becomes a little more conceptually clear here, because f of x less than means below the axis, f of x greater than means above the axis, and f of x equals to 0 would have to mean exactly on the axis, which is the x-intercept. Okay, well, these were some of the main ideas we were dealing with last time, and I think that's how we ended class, was doing some inequalities, right?
Yeah.
Okay.
The last answer was x-intercepts.
Yeah, the last answer is x-intercepts, or on the axis.
On the
F of x equals 0 means you're on the axis. So today is our last day for chapter 4, and in fact, I think we'll finish it fairly quickly, and then we'll have the rest of the class period to go over the practice test. I'm excited about that because I'd like to go through a few of the practice test problems with you so that you feel more prepared for the day of the test, which is after we get back from spring break. So next week, none of us have to come to Gateway. None of us have to. You can still come if you like. I'll still be here Monday, Wednesday from 12:30 to 2:30. I'll just be sitting in this room in the dark, crying. So if you want to come in, no, I'm kidding. I won't be here.
It'll be like a robot without power.
Yeah, exactly. All right, so then when we come back, then on Monday, when we come back, you'll all take your test in chapter 3 and 4. So we will definitely go over lots of questions from the practice test today, and that way you can all go home, you can practice. If you want another copy of the practice test, they're right here. Also, I posted the practice test online, so you can print out another copy. I also posted the solutions online so that you can look at those. Okay. Well, our joke for the day, did I already tell you about Waldo? Where's Waldo? No. So first of all, are you all familiar with Where's Waldo?
Yeah.
Probably we all are. Well, let's just be clear. Where's Waldo is a book, a children's book, or an adult book, I suppose, where they show you, here's Waldo, he's this guy in a red and white striped shirt, and then they put him in a scene, and then you have to get in there and look for him.
There was a sequel to this book.
There is?
Yes.
What's it called?
Where's Aldo's brother?
Oh, I see.
He's basically just sitting in a white page.
Oh, gotcha. That's funny. All right, so yeah, that's Waldo, and it's tough to find him. It's really hard to find him. That's the whole point, which is cute. Okay, so the joke. Why does Waldo wear stripes? He doesn't want to be spotted. He doesn't want to be spotted.
I'm usually good.
Yeah, does it make sense?
Yeah.
All right. So then, folks, here we go. We are now on some word problems. So let's tackle these word problems. Now,
Please tell us which one we're on, which package we're on.
yes, this is the chapter 4 notes packet. It's the end of the chapter 4 notes packet. The first page, thank you, Nadine, said chapter 4.0 notes. So it's all the way in the back. In fact, it's the last page. All right. Now, Valeria left. See, I always want to play pranks. Like, I think we should all leave. Just take our stuff, go to another room, and then when Valeria will come back, she'll be like, I'm down. Well, we move her stuff too, so she just comes in the blank room. She's like, what's going on? And then we're all in another room, a couple doors down. And she finally finds us. And we're like, we've been here all along.
That'd be great.
And she's like, this isn't our room. We've never come to class here.
I have a question.
That'd be
It's
great
not
when you
related to math.
Yeah.
What's the word that, like, say somebody has like an old coupon for something, and technically they're not allowed to use it, but the people let them. Like, what's the word? Like,
They honor the coupon?
honor. I guess honor. Okay. Yeah, I was thinking. Yeah. What I was thinking.
Validate? I don't know.
Yeah, that'd probably be the other one.
I don't know. Hector?
That's a great idea. The only problem I see with that is that we're taking her stuff without permission, which is illegal.
Yeah, it would be considered that. So yeah, that's how a good joke
Or
goes
we
wrong.
could just take all of our stuff.
Yeah, either way. Okay, back to the word problem. So first of all, everyone, are you familiar with this formula called D equals RT?
Yes.
All right, so D equals RT. First of all, are you also familiar with, this is just what the equation is if you solve for D. What's the equation if it's R equals or T equals? How do we find that? So let's say I want to solve for R. How do I get rid of the T?
You divide.
You divide it off. So I divide off the T and it would cancel, and now I have R equals D over T. Likewise, how would I solve for T? There you go.